Hey everyone, and welcome to this explainer. Long before satellites were casually beaming GPS coordinates directly to our smartphones, massive empires and transcontinental railroads were mapped out using pretty much nothing but the Earth's magnetic field. It's actually kind of wild to think about. So today, we're taking a practitioner's journey to uncover exactly how compass surveying works, from the foundational principles right down to the nitty-gritty of getting your gears set up in the field. Okay, let's dive right in and anchor these abstract ideas to our primary tool for the job, the prismatic compass mounted on a tripod. It's got this sleek cylindrical metal box, a magnetic needle perfectly balanced to align with the Earth's magnetic pull, and a prism for taking ultra-precise readings. Honestly, it's a total marvel of analog engineering. It's compact, it's incredibly portable, and it gets the job done. So, here is our roadmap for today. We're going to breeze through the core surveying principle, compare our compass choices, run through temporary field adjustments, tackle those pesky surveying errors, and finish up with the advantages and disadvantages. Let's get to it. Starting off with Section 1, the compass surveying principle. The absolute bedrock of compass surveying is a technique called traversing. Basically, traversing is just creating a series of connected survey lines. Now, if you're in a small, totally flat area, you might just measure rigid triangles using a chain. But what if you're dealing with a massive, highly undulating landscape that's absolutely crowded with thick forests or city buildings? That's when you use a compass to measure the magnetic bearing, or the angle of your line, and then you just measure the distance with a chain or tape. And a traverse generally unfolds in one of two ways. First, you've got a closed loop. Imagine you're mapping the boundaries of a large estate or a lake. You start at your first point, take your bearings and distances around your property lines, and eventually you connect right back to where you started. Then you have a linked traverse. This is more of an open-ended path. It is absolutely perfect for surveying a long, narrow strip of land, like if you're plotting the winding coastline of a river, or maybe laying out the route for a brand new highway. All right, moving on to Section 2, choosing the instrument. In the field, we generally choose between two primary instruments, the prismatic compass and the surveyor's compass. The big difference here comes down to how they actually read angles. The prismatic compass uses a whole circle bearing system. That means it measures angles continuously clockwise from 0 all the way to 360 degrees, with the 0 point sitting at the south end. The surveyor's compass, on the other hand, uses a quadrantal bearing system. This measures angles from 0 to 90 degrees relative to either north or south. So you'd read something like north 40 degrees east. Oh, and another key difference. In a prismatic compass, the graduated ring is attached directly to the magnetic needle itself. But in the surveyor's compass, that graduated ring is physically fixed to the box and rotates with your line of sight. But the mechanical difference becomes super obvious the second you actually look through the device. A prismatic compass features, you guessed it, a prism. This allows you to sight your target object and read the graduated ring at the exact same time. And here's a fun fact, because you're looking through a prism, the graduations on the ring are actually printed upside down, so they appear the right way up to your eye. With a surveyor's compass, there's no prism. You just have a simple slit. That means you have to do a bit of a dance, sight your target, and then physically shift your head to look down directly at the top glass to read the needle. Let's head out into the wild for Section 3, Field Setup and Temporary Adjustments. Before you take a single measurement, you have to run through 3 absolute must-do steps every time you move the tripod. Step 1 is centering. The compass has to be perfectly positioned vertically over your ground station mark. Think of it like dropping a pebble from the exact center of the compass box. If it hits the bullseye on the ground peg, boom, you're centered. Step 2 is leveling. You tweak the tripod legs or the ball and socket joint until the compass is perfectly horizontal. If it's even slightly tilted, the magnetic needle is going to drag and give you a completely false reading. Finally, step 3, if you're using a prismatic compass, is focusing the prism by moving it up and down until the numbers on the ring are razor sharp. Now, why does this matter so much? Well, skipping these steps is basically a guaranteed recipe for disaster. Spending just a few minutes performing these temporary adjustments prevents hours of frustrating, crooked map lines later on. A poorly centered or unlevel compass will fundamentally compromise the geometry of your entire traverse. So yeah, take the extra 2 minutes. Which brings us to Section 4, Navigating Surveying Errors. Because, let's face it, things don't always go perfectly in the field. Surveying is literally a battle against chaos, and errors generally come at us from 4 main directions. First, instrumental errors.
This happens when your gear is physically compromised, like maybe the magnetic needle got bent in transit or the pivot became blunt. Then we have systematic errors. These are consistent biases, like if you just fail to regularly calibrate your equipment. Next up are blunders. These are entirely human. We're talking about writing down a 6 instead of a 9, or accidentally kicking the tripod right in the middle of a reading. Finally, we have natural factors. Things like temperature changes can expand or contract instrument parts. But the biggest natural headache by far is magnetic declination, where magnetic north just straight up doesn't align with true geographic north.
So, with all those potential errors and headaches, you are probably wondering, in the modern age of GPS, high-tech total stations, and laser scanning, why on earth do we still use an analog magnetic compass? Let's break that down in Section 5, the final verdict. Truth is, the compass offers some incredibly distinct operational advantages. First of all, it requires exactly 0 electricity. When you are deep in a remote forest and your expensive total station batteries die, the Earth's magnetic field is still right there, ready to power your compass. It's also highly portable and incredibly simple to set up. But honestly, the most powerful advantage is that in compass traversing, each survey line is measured completely independently. Meaning, if you make a bad angular mistake on one line, that error does not compound and ruin the bearings of all the other lines in your map. And finally, because magnetic surveying has been the standard for centuries, it is literally the perfect tool for retracing historical property lines and old surveys. But we do have to be sober about its limitations. The main disadvantage is, of course, lower precision. A standard compass simply cannot compete with the pinpoint millimeter accuracy of modern digital tools. But more importantly, compasses are highly susceptible to something called local attraction. If you're surveying anywhere near iron ore deposits, steel structures, or even underground electric cables carrying a current, that magnetic needle is going to be pulled right off true magnetic north, making your instrument pretty much useless. Plus, as we mentioned before, it's always vulnerable to simple human alignment errors. And that brings us to the end of our journey. So how does understanding this foundational, completely electricity-free tool change the way you appreciate modern digital mapping? It is pretty incredible to think that the sprawling, complex maps of our past were meticulously drawn using little more than a magnetized needle floating on a pin. The next time you casually pull up a map on your phone, maybe take a second to remember the surveyors who navigated the world one bearing at a time. Thanks so much for joining me on this explainer. Keep learning, and I'll see you next time.